But that was not how my life worked today. Okay, other announcements. As always, your ALEX objectives are due on Monday. After class, I'm going to go back to my office, and I'm going to verify that what is assigned covers Monday's lectures and today's. So you have time. If you get stuck, so you're going to get increasingly, I don't want to say difficult, but some of the ALEX objectives are going to start to become a little bit more complex. If you get in a pickle, my recommendation would be to do them over the weekend so that on Monday from 12 to 2 you can stop in office hours where I'm just so happy to help. If you get stuck, I will sit there and work objectives with you until we figure it out. Mostly I sit there and hope that someone comes to my Zoom room. So like I'm not begging you to come, but I wouldn't be mad if people came. So don't forget you need a calculator. Your mini exams are here. They are graded. You will get them back at the end. We'll talk about it at the end. Your first chemistry in life is due September 29th. Ballpark half an hour. It will take you longer to figure out what it is you want to talk about than it should for you to write 300 words. I'm not asking for a novel. I'm not asking, if you bake something cool, I might ask for a link to your baked goods. So I'm but that's because I like to cook. I'm not asking for anything else. If you have questions about it, I'm happy to answer that. Any questions about these announcements? So, over the last several days, an increasing number of students have started to email me asking, what exactly do I need to memorize about this periodic table? It's a very fair question. Someone emailed me a blank periodic table that looked like this, that they had covered up each individual square. And we're like, so we're going to fill this out, right? And I didn't know how to write back, absolutely not. That periodic table right there, just like this, is what I'm going to give you. Just like, but readable, because it doesn't look very readable. The only difference between this and the green sheet is the name. So all I'm asking you to remember is that Fe is iron, and the word chlorine equals Cl. Just please do not waste your time memorizing anything else. And only the elements 1 through 86 minus the lanthanons. Whatever it says on here is all you need to know. Any questions about, yeah?
The last question said we need to memorize methanol and methane. I tried finding that all 8
Interesting.
This is a video that you sent me notes at the very end. I just took a screenshot of it.
It's like the last, and I know that because I, in fact, watched them before I reassigned them on, the fastest speed they would go, because then I don't hear myself. It's the third video, the last 30 seconds. But it is CH4, methane.
So those are polyatomics, or is this something different?
These are the hydrocarbons. Ethane, propane. Nope, that's 6. Thank you. C4. Thank you. And the corresponding alcohols, which is CH3OH, methanol. CH5OH, ethanol. C3H7OH, propanol. And C4H9OH, butanol. Yep. So what do I get for not using notes? You need to know these. If I pick something else, like octane, I'm going to give you the formula for that and say write the combustion for octane if octane is C8H, a lot of those. It's the same process as anything else. Good question. Other questions? Speaking of things, on the back of this green sheet, you are responsible for the polyatomic ions. It's probably the best way to think about that. If it is a single element alone, those follow the conventional naming rules. talking about things like ammonium, nitrate, nitrite, acetate, permanganate, cyanide, etc., etc., etc. All the ones where it's like oxide is O2-. Like, you do need to know that, but you're responsible for any element in the right parameters and the polyatomic ions on the back of the sheet. Question. Take a step. Yeah.
I scratched out all the Latin names, right?
Yeah, definitely don't learn the Latin names. I'm not that kind of scientist. Biochemists like normal names. Iron, iron 2, iron 3. There are other types of chemistry that use those names. I'm not that kind. I'm not going to ask you to memorize things that I don't know. I'll have to look it up every time if we're going to be honest. Other questions? You guys are always so quiet. So let's talk about chapter 3. We stopped here. Yes. Did we stop? We need to do these. So, to calculate the molecular weight, or the formula weight, or any of these, the way we do this, we're going to use our periodic table. So, in last class, we talked about how the atomic mass units of 12.007 or whatever for carbon is now 12.01 grams per mole of carbon. So to calculate the formula weight and or the molecular weight of either sucrose or calcium nitrate, so sucrose is C12H22O11. There are 12 carbons, 22 hydrogens, and 11 oxygens in this compound. We just need to total up the amount of mass that comes from any of these given elements. So it is 12 carbons, 22 hydrogens, and 11 oxygens. So 12 times 12.01, 22 times 1.01, 11 times 16.00. Together, that gives you 342.34 grams per mole. So 1 mole of sucrose equals 342.34 grams. So we can calculate both of those. Questions about the calculation for sucrose? Yeah?
When we take the mass, we only use the first 2 decimal points, right?
You're going to round to 2 decimal points. So the question was, do we just use the first 2? So for oxygen, it's 15.999. I think there's only 3 decimal places on here. Yeah, some of them have more. But we only need 2. So when we convert this, we're going to use our regular rounding of 5 and up, round up, 4 and down, round down. So this rounds to 16.00. And you only need 2 decimal places. You can bring them all along, but I'm only ever going to use 2, just so that we're all aware. The keys will only have 2. The downside, it's not a downside, well, that's a little bit. If you start adding in extra numbers here, what you're going to start to see is that your answers and my answers diverge. Sometimes by like 0.01, sometimes by 0.1. I will always trim to 2. My recommendation would be that you trim to 2 as well. Other questions? So calcium nitrate. We're going to do the same thing using the words to molecular formula. So we have 1 calcium, 2 nitrogens, and 6 oxygens. So 1 times 40.08. Whoa. 2 times 14.01, and 6 times 16. And this gives you 164.10 grams per mole. Unless explicitly asked, because I feel like this comes up often, you don't need to show this much work. You can just say the molecular weight in your calculations. Just feel like in here sometimes people ask, like, do I have to show that? Yeah.
I have a question. Can you pick a figure if you're not really applicable to these?
So in this case, because it's addition, you just should maintain the 2 decimal places at the end. In terms of a calculation where we're going to use this value is outside it's outside of the question, so you just use the values from the question. Good question. Other questions? We talked about Avogadro's number, right? Yeah. But we did not look at any of these, correct? Thank you. I appreciate the honesty of like, no, you did not. Let's talk about it today. Excellent. So in this case, we want to start to think about the ability, so our goal, where are we going on this adventure? I'm going to say, in this reaction, you started with 5 grams of this. How many grams of whatever at the end did you get? We're not going to get there today. We will get there on Monday. But this is the first best step. The ability to go from either grams to moles to atoms, atoms to moles, or moles to grams. Any of those, we can get to any of the others. So our first one says, calculate the number of H atoms in 0.350 moles of C6H12O6. So we're going to take our 0.350 moles of C6H12O6. And the first thing I'm going to do is convert into molecules. So in 1 mole of C6H12O6, there's 6.022 times 10 to the 23rd C6H12O6 molecules. In any one C6H12O6, how many hydrogen atoms are there? 12. Excellent. In one C6H12O6, there are 12 H atoms. When you plug this into your calculator, you should get 2.53 times 10. That doesn't look like numbers at all. Times 10 to the 24th H atoms. What questions do we have about this calculation? Yeah.
Why is the hydrogen?
So in the top question, it only asked for the number. It's a fair question.
What does that last term when fractions say? Because the screen's a little in the way.
Does that help?
Yeah.
Oh, I'm glad I've been lifting weights. This is not a permanent decision here, just as an FYI. But I'm more than happy to. All right. Everybody got it? Thank you.
It's really like my angle, so.
No, how far? Can you see here?
I can see up to the end of the. I mean.
I'm just going to draw a line and work on that side of the board.
C6. I can see C6 at the end.
About right here?
A little further.
That way?
No, the other way, but it doesn't matter.
We'll just leave it here.
Yeah.
Mostly, I think it's annoying to be in a room and be like, I can't see that. How am I supposed to do that? So thank you for telling me. I'm sorry that our newly designed small boards inhibit visualization. Other questions? Okay, so let's look at our second example that asks, how many oxygen atoms are in 0.25 moles of calcium nitrate? So in this case, pretty much the same type of calculation, just with different entities. So we're going to take our 0.25 moles of calcium nitrate. We're going to erase this too. And the first thing we're going to do is we're going to convert to calcium nitrate molecules. So in 1 mole of calcium nitrate, there are 6.022 times 10 to the 23rd calcium nitrates. How many oxygen atoms are in a single calcium nitrate? 6. So in 1 calcium nitrate, there are 6 O atoms. I'm going to be honest. Right now, we all know that that says 6 oxygen atoms. In like 30 minutes, if this was still up, you would think it said 60. On exams or keys, I try to write out the word oxygen just so that you're not like, where did the 60 come from? You may choose to do that as well. And I get 9.0 times 10 to the 23rd oxygen atoms. So what questions do we have about these types of calculations? Yeah?
When we round the scientific notation like a 9.0, we round it to the least amount of significant figures, right, in the whole equation?
So the question is, do we use the least number of significant figures in the equation? It turns out in this example, since the only number of sig figs you have is 2, that would be the deciding factor. The 6.022 times 10 to the 23rd is a standard. We're going to treat the fact that there are 6 oxygen atoms in one of those as also a standard. And so your sig fig should basically be determined by whatever values are given in the problem. I don't want to say no more, no less. And if I feel like it's hard to know, it might say in the question, like, use 3 sig figs or use 5 sig figs or whatever answer it is if I feel like it could be ambiguous. Questions? Any other questions? Yeah?
What if, like, often we get to getting sig figs wrong? Like, I know on Alex it counts completely wrong, but, like, on tests and stuff, will it be, like, count completely wrong?
Not unless the question is how many sig figs are in here, and then in that case it's different. It's usually 2.
All right.
Occasionally it can go up to 3, depending on what it is. But yes, typically what you'll see is a -2 and then a scrawl of SF, which just means sig figs. Any other questions? Yeah?
Do we have to write out the entire, like, the CA and every to for our work on tests? Will that be included as work?
You can use as little work as works for you. However, if you've done something and I can't figure it out, it's harder for me to give partial credit. I will admit, if you get the right answer and you have work, you get full credit. If you have the right answer and you have no work, I'm going to write a note that's like, maybe next time could you show something? Because I assume, right or wrong, that you just use your eyeballs and creeped around to get a random number. In this case, if you do something and you get the wrong answer and I can't follow your work, I'll have a harder time. But I will always show you more work than you have to show. So if I had to write this out, I don't know that I would include this or this, maybe some of this. But I probably wouldn't write it out all of the time. Or I would just put CN for calcium nitrate because it takes a long time to write that. Other questions? Yeah?
One thing I noticed in local as well found to be pretty harsh in terms of a transition was going from Alex to the main exam last week. Because it's well on Alex you essentially have an indefinite amount of time where you can drop. And we found it and we were like, oh wow, we're going at a pace that's much faster than what I could do
I try, sometimes I will give examples or give you guys an opportunity and I will give you X number of minutes. So the question is about how fast to increase your speed. So Alex is great, but you have an infinite amount of time. And so I think the other thing that we should be doing, in addition to our Alex work, is finding additional problems to work, whether that's hitting up SI, going to tutoring. I have worksheets. There are other example problems on my YouTube channel. There are book problems. Any of those are structured similarly to how you will find them on exams and other things. And so my recommendation would be to start spending time. Most problems, you should be able to read it, complete it in under 5 minutes. Some of them are less time, like this one here should probably take you less than 2. And so the more of them you do, not just on your calculator, but with a pen and pencil, the faster you will be. Any other questions? Yeah.
So I'm struggling to wrap my head around moles. Is 1 mole just always for any given atom, just Avogadro's number times that?
So Avogadro's number. If you go to the grocery store and I ask you to buy a dozen eggs, how many eggs, hopefully you bought eggs before, otherwise this doesn't work. How many eggs do you expect to come home with? 12. If you buy 5 dozen eggs, you expect to come home with whatever 5 times 12 is. I think that's 60. We'll go with that. Avogadro's number is basically a set unit. So any mole of anything, elephants, ants, potatoes, feathers, calcium nitrate, oxygen atoms, whatever it is 6.022 times 10 to the 23rd of those.
Okay, so it's not like a set weight, it's a set amount.
It's a set amount. So you can think about it instead of, so when you buy things in bulk, if you were to go to a bulk grocery store, which there aren't any here, but if you watch, like in larger cities, they have them, you can buy flour at Publix or Winn-Dixie in the container. You get the bag, it's usually 5 pounds. If you go to a bulk grocery store, you do it by weight. So in this case, it's telling you that you have this many number of those. And if your item is heavier or lighter, it can change the weight of that, but it won't change the amount. Well, it won't change the specific number. Does that help?
Yeah. Thank you.
Good. Other questions? So now let's start to think about the connection between grams and moles. So we're going to start with grams. How many moles are in some number of grams, and how many grams are in a quantity of moles? And then, you should have time to look at this, how many copper atoms are in a 100% copper penny. So that will go from grams to moles to atoms. So we're going to start here with our first example of 5 grams of sodium chloride is how many moles? So in order to convert from grams to moles, so grams to moles, we're going to use the molecular weight or the formula weight, depending on the type of compound. So we're going to take our 5.00 grams of NaCl, and we're going to multiply that by the inverse of the molecular weight. If you remember back in chapter 1, we talked about unit conversions, which were terrible. This is Gen Chem 1 unit conversion. We're going from grams to moles using a unit conversion because now we know that sodium chloride has a mass, X number of grams per mole. That's why we taught you guys how to do that. This is where we're going with that. So the molecular weight of NaCl is, in fact, 58.44 grams per mole. So now we can use here, so it's 58.44 grams in 1 mole of NaCl. And when we divide 5 grams divided by 58.44, we should get 0.0856 moles of NaCl. So what questions do we have about how we arrived at the number of moles of NaCl? Yeah.
Is there a difference between molecular weight and formula weight?
So only sometimes. For the purposes of this class, no. Molecular weight is for a molecule, formula weight is for an ionic compound. I will 100% of the time just flop between either one of those terms. And basically, I mean whatever the sum of all the masses is. Other questions?
Where did you get 58.44 from?
So this value is the molecular weight of sodium, which is 22.99. The molecular weight of chlorine, which is 35.45. Added together gives you 58.44. Good question. They are, and you do not need to memorize those. Just want to say that as many times as possible. How many of you feel, well, it doesn't matter. I'm going to give you, I don't know, 3 minutes. No, I'm going to give you 2. The mass of calcium nitrate is like the second problem we did today. I want you to determine what mass in grams is 4.33 moles of calcium nitrate. If you did not by chance write that down, the mass of calcium nitrate is 164.10 grams per mole. If you're having a panic, look at the units, follow the units. How's it going? I see some yeses. We'll give those of you who are still working another couple of seconds. So in this question, oh yeah, I said another couple of seconds. I should, in fact, wait those seconds. My bad. So we have our 0.433 moles of calcium nitrate. Oops. So from here, we need to convert from moles to grams. We're going to use the molecular weight, formula weight. And in this case, unlike here, we are going to multiply by 164.10 grams in 1 mole. This is the molecular weight, which you would have determined by adding up the sum of all of the atomic weights. And you should get 71.06 grams of calcium nitrate. So the reason we multiplied instead of dividing is because we want to make sure that we cancel our units. So in this case, the moles have to cancel with the moles on the bottom, so you get grams up top, which is different than here where we had grams and we needed to go to moles. What questions do we have about this aspect? Yeah?
So the answer is 466, right? Here, 71.066.
Nope. It should definitely only have 3.
Okay, I just want to make sure. And that's because we started with 368.
Correct.
Got it.
Yeah. Let me make a note. A minute. Other questions? So let's look at this other calculation. How many copper atoms are in a 100% copper penny that weighs 3 grams? So in this case, it's going to be somewhat similar to the 2 calculations on the slide before and the ones here. We're going to go from grams to moles and from moles to atoms. So we're going to take our 3.00 gram copper penny. So when it says it's 100% copper, it basically tells you that all of that weight accounts for copper. Sometimes in Alex, you'll see things where it'll be like, it weighs 5 grams, but only 30% is whatever that atom is. In that case, you would multiply this by 30% and proceed. The molecular weight of copper found on our periodic table is 63.55 grams in 1 mole of copper. If I want to go from moles of copper to atoms of copper, what number do I use? Avogadro's number. In 1 mole copper, there are 6.022 times 10 to the 23rd copper atoms. And this gives us 2.84 times 10 to the 22nd copper atoms. What questions do we have about grams to moles, moles to grams, grams or moles to Avogadro's number?
So you're saying if it's at 30% instead of 100%, you just multiply the 3 grams by 30%?
Yes.
And then from that, you plug that in and do the same thing?
Yes. If I felt confident in my ability to determine 30% of 3, I would tell you that, but I do not. It's roughly under 1 gram, but I don't really know how much under. Thank you very much. Other questions? Sweet. So this should say chapter 3, part 3, because this is the 3rd part we've gotten to. So we're going to do part 3 that says 4, and then we'll get to part 4 next week. So empirical analysis. So we've spent some time thinking about grams to moles and moles to grams. But we want to take a break to think about empirical analysis. So part of this is percent composition. Percent composition is the ability to determine what percent by mass something is. So percent composition is basically the mass of an element divided by the total mass. For example, if it is a compound, it would be the number of atoms multiplied by the atomic weight divided by the molecular weight. Multiplied by 100. That'll give you a percent value. This is basically going to tell you, for any compound, such as this down here, what percent by mass, or percent composition, is this based on the known molecular formula. So let's look at this first example. So in this case, this is the molecular formula for sucrose, but we want to calculate the percent by mass for carbon, hydrogen, and oxygen of this compound. So in order to do this, we need to determine the molecular weight. The molecular weight, in this case, I'm going to give it to you, and it is 342.34 grams per mole. So, for each of these, we're going to start with carbon. And the percent by mass is, there are 12 carbon atoms, and they each weigh 12.01 grams per mole, divided by 342.34 times 100, and that's going to give us 42.10%. So I took the mass of carbon, how many moles of carbon there are in this molecule, 12 carbons times 12.01, divided by the total mass. Next up is hydrogen, which is 22 times 1.01 divided by 342.34, and that gives you 6.50%. Now oxygen, it turns out that there are two ways you could calculate this. Basically, you could ride the same train that we've been riding. 11 times 16.00 divided by 342.34, and that gives you 51.40%. You could also assume that if the total mass is accounted for here, for oxygen or whatever your third component might be, you can take 100 minus 42.10 minus 6.5, and that should give you 51.40%. Because we know that the total composition is these three things. You could do it either way. There's no more right or wrong method. It's just two different methods. What questions do we have about this?
Are we going to get that total weight on the
No, more than likely that would be part of the question. Some will come with it, some will not. Make sure you always read the whole question. If it's not, it would be accounted for in the points. Like part of your, I don't want to call it a reward because that sounds terrible. But I would give you credit. So if all you did was calculate the molar weight, and then you're like, I don't know what else to do, you could get points for that. You would almost always get points for that on mine. So if you, or hypothetically, if you got this and you got, I don't know, 500, and you did all of this, you might get all the numbers wrong. Nothing on yours would look right. But you would lose points for this, but earn partial credit for the ability to know what to do, even though something went quite wrong. Yeah?
That's actually what I ended up doing. So I tried doing this before, and I ended up putting 14
Okay.
into hydrogen. I don't know why, but yeah, that messed it up.
So I'm a big fan of partial credit. I think whatever it is that you know, I want to reward you for that. Just as an aside. So if you are looking at the slides, we're going to skip this slide and start here. Yeah?
So is the total weight like in the problem?
No, you would have to calculate that. So on this one, you could use the molecular formula C12H22O11. It's okay. Yes. It's a fair question. We're going to skip this one. We're going to do this. The slide should be in a different order. Clearly, I screwed that up, so we're going to do this one, then go back. So, if I tell you that the molecular weight of potassium platinum chloride is 485.98 grams per mole. I'm going to give you 2.5 minutes to acquire the percent composition for both potassium and platinum using the molecular weight of 485.
this was the other method, I was
Yes.
right this time. Okay.
That's totally fair.
Thank you.
Yeah. If you have questions, let me know.
It's always times by 100, right?
Yes.
Okay.
To make it into a percent value. As long as it says that and you can use non-internet line. Yep. So on this one, if it asks us in the question, it will just tell you how many decimal places. Because that question, after this one, there's no. So in this case, I would use 2 decimal points, similarly to a periodic table. So if this was a high and I didn't tell you, I would take that many or a few sig figs. I don't want to say within reason, but within reason. So on here, I would suggest that you use 2 decimal points in all of them. How's it coming? Good, good. I like hearing. I think I got answers. Does anyone need additional minutes? Excellent. So in this case, having the known molecular weight for platinum, we're going to take our 1 molecule of platinum times 195.08 and divide that by 485.90, multiply by 100, and that's going to give us 40.14%. For potassium, which is K, 2 times 39.10 divided by 485.90 times 100, and that's going to give us 16.09%. While I was wandering, someone asked about significant figures. In this question, there are no sig figs in the problem. There's no value present. So I tend to keep 2 decimal places. On an exam or a mini exam, this would have said, use X number of sig figs or 2 decimal places in the answer.
I was going to ask why you're dividing by 0.90. Or 485.90.
I don't know. Because my 8's turned into 0s. It's a good question. Yeah?
Wouldn't you round 16.09 up to 16.10?
I only have 2 on my sheet, so you would only round if the next value after that was something else. So if you plugged it in and you got 16.098, then it would round to 16.10. But if the value after that is something else, so you just round to this one. What?
Why do I not have that?
It's because rounding can get tricky. Other questions? So now we're going to pop back to slide 19, then we will skip 20 and go forward. So percent composition feels kind of like a weird detour into a calculation that doesn't mean anything. Yeah?
I do have one more question.
Well, I have an answer then.
Great. So we were taking all of our weights 2 decimals. So if we have kept 4 significant figures for every number we use throughout our calculations, or just for the answer,
this one?
Yes.
It wouldn't really matter. And I will only look at your sig figs on your answer. So I tend to bring, I call them like trailing digits. I bring my trailing digits along until the end, and then I chop them off.
Okay, cool.
So if you prefer, let's be honest, almost none of us type in the calculator, write the answer down, move and do the next part. I tend to put it all in my calculator and then at the very end assess what it needs to be. That's really all I will ask you to do. The only time you'll find that that gets weird is on Monday when people start looking at more longer complex equations. Then people they stop their calculation in the middle. But I don't. I would just put 2 times 39.10, enter, divide by 485.98, answer. Where's that piece of paper I want? There. Any other questions? So the reality is we talk about percent composition because we can use it as a tool. If you watch like crime dramas, they eventually go to the lab, they inject some weird sample, and it like beep, 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 and then it talks to them. That's not how this rolls. In real life, you put it in, you wait a long time, and then it gives you a number, and that's it. So if you have an unknown chemical compound, a white, substance, and they want to know, is this cocaine? There's 2 ways you can test for that. 1, they actually have a colorimetric test where it basically reacts. Or 2, you can send it to the lab. And when you do that, you get 2 parts of data. You can get the molecular weight of this compound and, in a different assay, the percent composition. Together, those 2 data points can tell you what you have found. So the percent composition can tell us the empirical formula. So in this case, we're going to start thinking about how these fit together. So first, we're going to talk about how we can convert between molecular formulas and empirical formulas. So if we have an empirical formula, or we have a molecular, so in this case, we have a molecular formula of C2O2, not a real molecule. What is the empirical formula? CO. So in this case, we know that to go from the molecular formula to the empirical formula, we just need to divide by 2. If we had the empirical formula and we had the molecular weight, it turns out that we can figure out what this value is. If we divide the molecular weight by the empirical weight, this should give you a whole number. And that whole number is the conversion between empirical formula and molecular formula. For example, the molecular weight of our C2O2 would be, I think, 88. Let's double check that. Not close at all. 56.02, which is 2 times 12.01 plus 2 times 16.00. If we divide by our empirical formula, which is 12.01 plus 16, which is 28.01, this is going to give us 2, which is a whole number. So we can, if we have the empirical formula, we can determine the empirical weight using a different analysis. So the molecular weight comes from the problem. And now beyond the second example. This is going to allow us to determine the molecular formula. If you know the empirical formula is CO, and you know that the conversion between empirical and molecular is 2, that tells us that each of these subscripts should be multiplied by 2. Questions? Yeah?
So the empirical weight is just the weight of the elements by themselves?
Well, in this case, the empirical formula is CO. It's okay, good question. So if this is our empirical formula, and we're trying to find the molecular formula, because we're going to use the percent composition to determine the empirical formula, and then we're going to use the provided molecular weight to calculate the other.
So then, in theory, there are going to be times that the empirical weight and the molecular weight are going to be one and the same when there's like only one of a certain
Yeah.
atom present.
So it's possible that the molecular weight and the empirical weight are the same when the molecular formula and the empirical formula are the same. So CO2, if you were to do this analysis, the empirical formula and the molecular formula are the same.
So, for instance, if we use this C6H12O6, so the empirical formula would be CH6O.
Uh-huh.
So that's divided by 6.
Yes, so if you did the same analysis, that would give you a whole number of 6. And then you would multiply the subscript. We are going to do an example on this. This is not the only, I'm not just going to tell you this and move on. Just so we're all clear. So we're going to come back to this. But let's look at a compound that is 74% mercury and 26% chloride. So if I have, so we're looking at this bottom part of the slide. It says, if we have a compound that is 74% mercury and 26% chlorine by mass, what is the empirical formula? It turns out that that feels like a really complicated, like, oh my goodness, we're going to have to do 10 things. There are 3 steps, and 3 steps only. And the first step is the easiest. That makes it sound like some are hard. None of these are hard, there's just 3 steps. Step 1, we're going to assume that you have 100 grams. So I like to call this the 100-gram assumption. We're going to assume that you have 100 grams because it makes the math easy. 74% of 100 is 74 grams. I like to cut down on all unnecessary mathematics. So for mercury, we have 74.0 grams. For chlorine, we have 26.0 grams. Okay, looking good. So step 2. Feels like it's going to be tricky. It isn't. We're going to convert to moles. Using that same technique that we used earlier in lecture where we divide by the atomic mass. So for mercury, we're going to divide by 200.59 grams in 1 mole of Hg. That's going to give us 0.369 moles of Hg. For chlorine, we're going to divide by the molar mass, which is 35.45 grams in 1 mole of chlorine, and that gives us 0.733 moles of chlorine. Now comes the last step. Again, feels like this one's going to be complicated. Not really. Step 3 is we want to divide by least moles. Because we're looking for the molar ratio between these. Ratios are some quantity divided by some other quantity. So we're going to divide by 0.369. And this is going to give us 1. This is going to give us 1.98, which is so close to 2. So that tells us for every mercury, there have to be 2 chlorines. So our empirical formula is mercury chloride and HgCl2. What questions? Yeah.
For the HG or the is it times or does it equal that and equal 1?
So the 0.369 we divided by 0.369.
Like the sign before it,
This?
that's an equal sign.
That's an equal sign. Sorry, I didn't know where we were. Other questions? Yeah.
At what point would you say it's close enough for the thing is two?
Plus or minus 0.05. The next example is going to give you an instance when it's not a whole number, and the example after that I'm not sure we'll get to, but we're going to try. We already did this one. So ascorbic acid is 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. What is the empirical formula? So determine that, and then, using a different analysis technique, the molar mass was determined to be 176, so that's the molecular weight. What is the molecular formula? I'm going to ask a question. Do you want to try by yourself? I'm getting a few nods, because the alternative is that I just do it on the board. Okay, I've seen enough people give the try. I'm going to solve it for you. I'm not going to just abandon you here. If you have questions, please let me know. I will move out of your way. I'm sitting on the board. You, sorry. No, use them exactly as is. So you assumed it's 100 grams, and if you added these three up, they should add to 100%. No, good question. I'm going to erase the work here so we have a working place.
So, sorry, I didn't have a lot of room on my paper. So.
No, you're fine. I will wait. How many of you have at least made it somewhere down the pipeline? How many of you are finished? Excellent. I'll give you guys about 30 more seconds, then we'll work on this. So in this case, we're going to follow the same plan. We're going to assume that we have 100 grams. In this case, in the problem, it gives us the percentages, and we can directly convert those to weights. So in this case, we have 40.92 grams of carbon. We have 4.58 grams of hydrogen, and we have 54.50 0.50 grams of oxygen. So that's step one. Step two is we want to convert to moles. We're going to divide by 12.01, and that gives us 3.41 moles carbon. We're going to divide by 1.01 in 1 mole, and that's going to give us 4.53 moles of hydrogen. We're going to divide the oxygen by 16.00 in 1 mole, and this gives us 3.41 moles. So from here, we're now going to do the third step, divide by the least moles, which is different than the one that I just erased, where they were partial values. So in this case, divide by 3.41, divide by 3.41, divide by 3.41. These both give you 1. And you may have gotten 3.407, 3.411, whichever one is the smallest. Even though they're like super close, you just gotta pick one. That gives you both 1. This one gives you 1.33. So previously someone asked, well, how do we know if it's really close? When you get an easily identifiable fraction, thirds, quarters, fifths, that's it, half. You should convert that to a fraction. So this is equal to 4/3. And in order to make this into a whole number, we're going to multiply all 3 of these through by 3. So we're going to multiply by 3, multiply by 3, and that gives us 343, to where our empirical formula is C3H4O3. What questions do we have about this part? Yeah.
So, I'm sorry, I just got lost on the last part of why we multiply by 3.
So we need these to be a whole value, because we don't, in Gen Chem 1, have any compounds where it's 1 mole of carbon, 1.3 moles of hydrogen, and 1 mole of oxygen. So you are multiplying through by the denominator in all of them in order to make that a whole number. If you are not easily identifying a value, if you're ending up with like 70 seconds or 70 thirds or something else, something has gone wrong in your calculation. They really should be whole numbers, likely under 10, just as an aside. Yeah?
I just want to talk about how I did this with you for a second. So I did the percentage by mass. I don't see that I ever converted to moles. My answer came out to C6H8O6.
So you only have the molecular formula, because you multiplied 176 by 40.92.
Right. And then from there,
So that
I
answers,
ratio into the atomic mass.
What you did gives you the molecular formula. But nowhere in your calculation did you acquire the empirical formula.
Right.
You can go around the clock this way, or you can go around the clock the other way. Your method totally works. Alex likes that method. It just doesn't give you the empirical formula. You would have to either come up with a different way how to do that.
So then, for the empirical formula, since I've got the molecular formula and it's a whole number, could I just look for that whole number and divide from there?
You may not get as full of credit if you don't do all those steps, because you still need to do the last part of the calculation. So we want to be able to convert our empirical formula to a molecular formula. In order to do that, we're going to use the molecular weight from the problem of 176. And then we're going to divide that by the empirical weight, which is 3 times 12.01 plus 4 times 1.01 plus 3 times 16. And that gives you 1.99, which is close to 2, which gives you what you found for the molecular formula of C6H8O6. So as long as there are different ways that you can get to a similar answer. my recommendation would be to go this way, because sometimes it will only ask you for this, and it won't provide the molecular weight. In which case, you'll have to do the 100-gram assumption. If you're given the molecular weight, that method will get you there. What other questions, if that method made no sense to you, you can just pretend that no one said anything. What questions do we have about this?
So is that the actual answer to C6, D8, O6?
It is.
You have to still do all that to the right, but then that will give you your answer right there.
Yep. This piece right here is the molecular formula. This is the empirical formula. On the mini exam, this would be where I would ask you like A, B, C, D. It would be very clear that I'm asking you for multiple different answers along the way. Hypothetically, let's say you did this. You got, I don't know, 3.5. This has to be a whole number. In your mind, in your little chemical brain, you're like, no, this is the wrong answer. You will get almost full credit if you write down, I must have done something wrong. This should have been a whole number, and then picked any old whole number and multiplied it out. Because that tells me that you got the concept of what this was supposed to be. Not that you just knew that you had to divide things and hope for the best. Questions?
So to go from C3H4O3 to C6H8O6, we just take 2, multiply it by the...
Yeah. This is, so if I gave you this, and I told you it was a molecular formula, you could determine the empirical formula, right? You would divide by 2 and get that value. So now we're just going in the other direction. So, do this example over the weekend. We will solve it first thing. It is slide 22, but I want to talk about your mini exam before we roll out. Okay, couple of things. Your top 4 of 6 scores will count. Canvas will not drop any until we have taken 4 of them. Here's why. Canvas will drop it if you made a perfect score. You got a 105. It will also drop it if you only got 5 points for writing your name on every page. Canvas is not that smart. It's like, oh, must drop 2 scores. You would never get points until mini exam 3. So, if you have scored in the red zone, below a 57, you need, between now and mini exam 2, to determine how best to study for this course. If you had a hard time finishing, my recommendation is to work more example problems. Because after mini exam 2, by September 30th, we need to make a decision as to whether or not you need or should go to the tune-up course. So this is going to give you an opportunity to change your destiny. If you're in the red, you want to go to the green. I want to say this. My name is Dr. Malcolm, and that is my grade scale. If you look at that, a 58% is passing. Please do not come to my office crying that you made a 71. That is a B. Like I don't know how to, because it happens every time. Someone's like, this is not happening. Those are the real numbers. That's what it will be at the end of the semester. So this is what they are. I'm going to set out your scores in just a second. Let me